So, in one type of nuclear power station, the reactor core can be made of graphite, into which fuel rods and control rods are inserted. The graphite is known as a moderator. What is the purpose of the moderator? Yeah, by what means? How does it do this? It absorbs the neutrons, stopping a chain reaction, stopping it going, what's the word when there's too many neutrons? Supercritical. Oh look, I've just gone to the next part. What's the purpose of the control? Oh no, control rods. Control rods are very similar. What's the purpose of the control rods? Yeah, the control rods can be adjusted to control the number of neutrons being released. In other words, to control a level of activity. You can, if you fully drop the control rods, you stop all the activity by blocking all the neutrons being released from the fuel rods. So anyway, what is the purpose of the control rod? The purpose is to regulate or control the release of energy. That's its purpose. Notice the question said purpose, not how does it do it or by what means. It just says what's its purpose, what's its job. So the job of the control rod is to adjust the level of activity, to regulate the power output. Basically a big control dial. Now, they want you to calculate the energy here. How can we do the next part, part B? What do we need to do here? Yeah? Well, put it into what? Like, which equation?
The action.
Yeah, but what formula are we going to use here? Yes? No.
Oh, okay.
No? No, are we having trouble with this next one? So I'll tell you how to do the next one. Please listen. Look at me. So what's happening here is you have uranium-92 and a neutron is fired at it. When the neutron is fired at the uranium-92, it becomes, I think KO's krypton, barium, and then 3 neutrons and some energy. The mass of the krypton, barium, and neutrons is in fact smaller than the mass of the uranium plus neutron. Where does this missing mass go? Energy. E equals mc squared. So our first job is to work out the loss in the mass. So let's do that. The mass before, that equals 235.0439 atomic mass units. I'll just write ATM. Atomic mass units. Plus 1.0087 atomic mass units. Can you, what's this please? Can you give it to me on the calculator? Daniel, go for it. And we will get that one later, but right now we'll just call it ATM. 236.0526 atomic mass units. Afterwards we have our krypton 91.8976 plus our barium 140.9136 ATMs, yeah, plus 3 neutrons, 1.0087, and this is atomic mass units. So what's this number, please? Yeah, you have to be very exact here. 8373 atomic mass units. Therefore, the lost mass is equal to this number minus this number. What's that? 0.00, so 1 point what? It's not quite 1, is it? It's like 0.21 atomic mass units. Sorry, I just wrote ATM. That's atmospheric pressure. I should have wrote AMU. So I was doing atomic atmospheric pressure with intake 2 yesterday. These are all, what's the unit here? Atomic mass units. But you did that thing again where you didn't correct me and you just let me write ATM all the way. Just let it be, okay? Now, Daniel, you were asking me how do we find atomic mass unit? It's actually a constant in the formula book. So here we should convert this into kilograms. It is atomic mass unit is 1.66 times 10 to the minus 27 kilograms. So what's this, please? What is it? 3.57 kilograms. Now that's how much mass was lost. This mass was converted into energy, which they call Q in the question. So the energy is mc squared. So that equals 3.57398 times 3 times 10 to the 8 squared. This is going to be a huge number. This is speed of light, isn't it?
6.21.
Oh, sorry, I left out the 10 to the minus 28 as well, which I'll just stick at the back here.
3.21.
Yep.
Times 10 to the minus 216,583.
Yep, times
10 to the minus 11.
joules. Now we should convert this into maybe like nanojoules or electron volts, yeah. Although they don't say it, I'll just convert into...
Where did you get nano? No.
This is wrong?
No. Yeah. So quick.
so quick to joules, aren't they? 10 to the minus 11 joules. No, I won't bother converting it into nano because it'd still be quite small in nano. So the answer is 3 point... No, but the fact we actually... That's the answer there. Now, I know this seems like a very small number, but this is actually quite large because this happens for each neutron that hits the uranium and turns it into barium and krypton. Because remember we said the neutron hits the uranium and it splits the uranium into barium, krypton, and then 3 neutrons. This total mass is less than the mass beginning to make energy. And by the way, if 3 neutrons have been released, then how many more processes can happen after this? 3 more. But then after that, 9 more. So you can see that if too many neutrons are being released, very quickly a chain reaction becomes you are no longer alive.
Or just energy released 2 times.
No, but this is actually quite large because this is for each uranium atom. And there's a lot of uranium atoms. Yeah, uranium atom is, only about this big. So there's a lot of uranium atoms in 1 kilogram of uranium. A lot. Like, what's it going to be, 10 to the 20 or something, isn't it? A lot.
So it's important to make transit to electron volts to do it by IE.
Did they ask for electron volts? No, but if they did ask for electron volts, you divide this by E. Yeah. Get out of here.